G'day, welcome back to Mathematics for another HSC maths lesson. Today I'm filling in a few more gaps in my Extension 1 HSC playlist. So I'm going to be doing a couple videos on differential equations over the next few weeks. Starting off with this first lesson as just a bit of an intro to what a differential equation is, showing you how we solve them, and setting up the sort of form and function for the next few examples. So without any more rambling, let's talk about how to solve a differential equation. Here is our first one. We have dy on dx is equal to 2x, and we are going to solve this differential equation. Now, I know you may be looking at this and just thinking, can't we just integrate it and go from the derivative to the original? And you'd be correct, but I'm going to show you how we're going to set this up and solve it in the structure of a differential equation. And this is going to be helpful when we are trying to rearrange and solve more complex differential equations in the later part of this video and in future videos. So here's how we're going to set it up. We are going to multiply the dx across the right hand side. So we have dy equals 2x dx. Now we're going to take both sides of the equation and we are going to, and keep in mind now that on the left hand side with the dy, it's like a 1 dy. That 1 was invisible, but it's still there, still very important. Okay, taking both sides of the equation and integrating them now. So on the left, we have the integral of 1 with respect to y. And on the right, we have the integral of 2x with respect to x. Now, integrating 1 in terms of y turns it into y with a constant. And on the right, the integral of 2x is x squared with another constant. Now, we don't have to do two constants on both sides of the equation because these two are going to merge together and just form one constant. So from now on, we're just going to do one constant. It doesn't really matter what side you put it on. You can put it on whatever side is more convenient to you, but either way, we should be working towards the same solution. So we'll just say y equals x squared plus c. So what this gives us is a variety of solution curves. Depending on what our constant is, it's going to shift our x squared value up or down. So all of these different colored curves are valid solutions to this differential equation. So a way we like to display all this family of curves, all these different possibilities for our solution is with this thing called a slope field. Okay, so the slope field we calculate by calculating the gradient of our differential equation at a single point. So what I mean by that is, if I let x equals 0 in this equation, I get the dy on dx is equal to 0. So that means wherever I have an x equals 0, I'm going to draw a horizontal line to represent a gradient of 0. Okay, gradient of 0 is a flat line. If I let x equals 1, I get dy on dx equals 2 times 1, which is 2. So wherever my x value is 1, I'm getting a derivative of 2. And so I'm doing a little line segment with a gradient of 2 to show the behavior there. So as x is becoming more positive, the gradient is increasing and becoming more vertical. Towards the left, it's the same thing, but we have negative gradients becoming steeper and steeper. Now, what this slope field allows us to do is to visualize a different solution depending on our conditions. So let's say our conditions was we want a solution going through this point here, which is where x is minus 2 and y is 0. We can look at that point and we can trace through it, and we're just kind of going to go with the flow of the slope field and sort of draw a curve in line with these tangents. So we're sloping down here. As we get to 0 in the middle, we are flattening out, and then over here we are increasing. So this is a really common thing we need to do in the Extension 1 course, where we're given a slope field and we're given a point and we need to draw the curve. And again, it's a little bit more art than science, but you're just kind of trying to go with the flow, follow the pattern of the gradients and draw your curve. Takes a bit of practice, but once you get the hang of it, it's really fun. Okay, let's go back to today's focus, which is just solving differential equations and getting comfortable with the algebra. Let's go on to another example. We have the gradient of the tangent to an unknown curve is given by 1 over 1 plus x squared. The curve has a y-intercept of 1. Find the equation of the curve. Okay, so if this here is the gradient of our tangent, we can interpret this as 1 over 1 plus x squared is our derivative. So we're going to write dy on dx is equal to 1 over 1 plus x squared. Now, we're going to solve this in a similar form to the previous example, where we're going to put the dx across to the right-hand side right here. That leaves us with dy on the left, and you can write 1 dy if you so choose, and we're going to integrate both sides. So pushing the dx across, integrating both sides, we now have the integral of 1 in terms of y, and we have the integral of 1 over 1 plus x squared in terms of x. Okay, so on the left-hand side, the integral of 1 is once again just going to be equal to y. On the right, we can integrate this using inverse tan, okay? The derivative of tan inverse, or arctan, is 1 over 1 plus x squared. So using that logic in reverse, we can say y is equal to tan inverse of x with a constant. Like I said, no need to put a constant on both sides. We can just group them together as one constant on the right-hand side or the left, whichever one you prefer. Now, because this question, I'm trying to end up with an equation of y equals, that's why I put my constant over here, so it's sort of out of the way. Okay, now we're going to use our initial conditions or our extra information in the question to figure out what this constant is. It says we have a y-intercept of 1. I can interpret that and saying that when x is equal to 0, it means that the value of y is equal to 1. So x is 0, y is equal to 1. Let's substitute that into our equation, and we get 1 is equal to tan inverse of 0 plus the constant. Now, tan inverse of 0 is just 0, so we get 1 is equal to 0 plus c. That tells us our constant is 1, and we can sub that back into our equation over here and get our answer of y equals tan inverse x plus 1. Okay, let's do another one of these in terms of x, and then I'll show you some more examples where we're going to be solving in terms of y instead and why that's a bit more challenging. But one more similar to this one. Okay, finding the particular solution of this equation, given that our condition is that when t is equal to 0, the value of x is equal to 1. So this is x evaluated at t equals 0 is equal to 1. We have dx on dt is equal to t over t squared plus 1. Okay, running through the structure once again, we're going to multiply the dt across to the right-hand side, leaving us with 1 dx on the left-hand side. Integrating both sides now. On the left-hand side, when we integrate 1, we're going to get just the variable x. On the right-hand side, if this was a 1 over t squared plus 1, it would be very similar to the last question where we were using inverse tan. Because this is a t on top of t squared plus 1, this is something we can use logarithms for. So we're allowed to integrate a fraction using logarithms when the top of the fraction is the derivative of the bottom. Now the derivative of the denominator is 2t, so we're going to fix this by putting a 2 on the top and putting a half out the front. So half times 2 is just 1. Left-hand side has been integrated to x, and now we can integrate the right-hand side using a natural logarithm. So we do the half out the front, natural logarithm. Don't forget your absolute values, and it's the logarithm of the denominator, t squared plus 1, with our constant. Okay, now we're going to figure out what our constant is using our conditions. So we know that when t is 0, x is equal to 1. So let's use that information. We have 1 on the left is equal to a half of log of 0 squared plus 1, which is just log 1. And then we have the plus c on the end. Now, pretty conveniently, logarithm of 1 is always equal to 0. So we have 1 equals 0 plus c. So we once again get that c is equal to 1. We can put that back into our equation over here, and we get x is equal to half and then t squared plus 1 plus 1. The question didn't specify whether we need to leave our answer in terms of x or t, so we're just going to leave it like this. If we needed to make t the subject, we'd do some rearranging. Wouldn't be that difficult, but if the question hasn't asked for it, let's not do extra work. Let's just move on and focus on something else. Okay, example 3 is a specific type of question where we have a differential equation and we have already been provided the solution and we're asked to show that this is a solution. Now, the reason I'm showing you this is because there's a shortcut you're allowed to take here. If you're being asked to verify that this equation is a solution of this equation here, we don't need to solve it, okay? Because we already have the solution. All we need to do here is show that this solution works in this equation. So the way we're going to do that is we're going to show that y equals 10x works on both the left and the right-hand side of this equation. So let's have a look at that. On the left-hand side, if y is equal to tan of x, we're going to do dy on dx, which is the derivative with respect to x, and tan differentiates to sec squared. So the left-hand side is equal to sec squared. Let's see what the right-hand side does. On the right-hand side, if y is equal to tan x, of course, our solution, if we do 1 plus y squared, we'll be doing 1 plus tan squared. And now, if you know your trigonometric identities from the advanced course, you might recognize that 1 plus tan squared is another way of writing sec squared. That is a known identity from the advanced course. And so we've shown that both the left-hand side and the right-hand side are equivalent to sec squared. So therefore, left-hand side equals right-hand side. And we've proven that y equals tan x is a solution of this differential equation. Okay, moving on to what is probably the more challenging part of this intro, we're going to be looking at equations where the right-hand side is in terms of y instead of x. So the issue here is that I cannot multiply this dx across here and then integrate, because I'll be integrating y with respect to x. So I'd be mixing up my variables there and it wouldn't make sense. So when we see an equation of this form where the right-hand side variable is the top of our fraction on the left-hand side, The first thing we're going to do is we are going to take the reciprocal of both sides. We're instead going to look at dx on dy. So flipping the left-hand side upside down looks like this. If we take y and flip it upside down, we get 1 over y. Now we're going to approach it in a similar fashion to the previous examples, where I'm going to multiply the dy across the right-hand side, leave the dx on the left with the 1, and now we can integrate both sides. So I've got the 1 with the dx's, but more importantly, I've got the y with the dy's. So getting your variables with their right d's is, really key skill for this initial lesson. Okay, now integrating the left-hand side, integrating 1 with respect to x is just going to give us x. On the right-hand side, we can integrate 1 over y using a logarithm once again. So we're going to have x equal to natural logarithm of the absolute value of y. If you want to put your plus c on the right, you can. I've decided to put mine on the left. And what we're going to do now is we are going to rearrange this equation just for fun. We're going to try and end up with y equals as we're used to seeing with our equations. So on the left-hand side, on both sides, I've raised them to the power of e. The left-hand side is now e to the power of x plus c, and the right-hand side is e to the power of log y. The reason I did that is because e to the power of log are inverse operations, and these are going to basically cancel each other out and leave me with the absolute value of y. On the left-hand side, a trick I've used here is that because I've got my powers plussing, I can split these up into a product. So e to the x times e to the c is the same thing as e to the power of x plus c, because when we multiply, we add the powers together. I'm just using that logic in reverse. Now, the reason I'm doing this is just to neaten things up a bit, because e to the power of c, e is a number and c is a number. So e to the power of c is just a number. I don't really know what it is. I'm going to give it a new label. I'm just going to call it a. Okay, because we have the absolute value of y, we're just going to say, depending on what e to the power of c is, well, e to the power of anything is positive, so that's convenient. So because of that, this being positive right here, we don't need the absolute values anymore. We just have a as our placeholder constant for e to the power of c, put that in front of e to the power of x, and now this is our best looking solution to this problem. So again, because I had dy on dx as our starting point, it was a good idea to leave my answer as y equals something in terms of x. Okay, let's do a couple more of these to get a bit more comfortable before we finish off for today. On to example 5, we have solved this differential equation given that y evaluated at x equal to 0 is equal to 5. Okay, so similar to the last example, the right-hand side is all in terms of y, and so to evaluate this properly and get my dy over here, the first thing I'm gonna have to do is take the reciprocal of both sides. So flipping the left-hand side upside down gets me dx on dy. Right-hand side is now 1 over negative 4y plus 3. Now I can do the same trick as last time, where I can multiply the dy across and then I can integrate both sides. So I've got the 1 dx on the left still, putting the dy across, and now we're going to integrate both sides. While I'm doing that, I thought it would be convenient to bring the negative quarter out of this fraction and just bring it out the front of the integral. Okay, always bring constants out the front if it makes your life easier. And now we can do some calculus. On the left-hand side, 1 is going to integrate to x, and the right-hand side, we've got negative a quarter out the front of this, and this fraction can be integrated once again using a natural logarithm, which we're going to be using a lot of in this topic, because the top is the derivative of the bottom. So we have x plus constant on the left, and on the right-hand side, we have negative 1/4 natural log of y plus 3. Okay, now we should probably figure out what our constant is. If you want to rearrange to make y the subject before you figure out your constant, you are welcome to, but I think it's a little bit easier to find your constant sooner rather than later, and that's just speaking from experience. So let's dive in and say, if x is equal to 0, y is equal to 5. So on the left-hand side, I've got 0 plus c. On the right-hand side, I have negative 1/4 log of 5 plus 3. That gives me c as a value of negative 1/4 log of 8. And now I can put that back into my solution over here, and then I can try and tidy things up and make y the subject just for a bit of fun. So the left-hand side is now x minus 1/4 log 8, and the right-hand side is the same as before. Now what I'm going to do next is I'm going to multiply everything by 4 just to make the equation a little bit neater and easier to handle with. I've also multiplied everything by negative. So x has become negative 4x. This logarithm term has become positive and now has a coefficient of 1. And a similar deal over here. So positive here, negative here, just makes life easier. Now, when I see two logarithms in an equation, I always think, how can I combine these together? Hey, what if I minus the log 8 over here? Because I have some log properties I can use when logarithms are adding or subtracting. When I have a logarithm, like for example, if I had log A minus log B, we can combine these together in a fraction and do log of A over B. Okay, those are the log properties you should have encountered in the prelim course. If you're a bit rusty, I've got plenty of videos on logs to help you out if you have no idea what's going on here. But the right-hand side turns into natural log of absolute value y plus 3 over 8, and the left-hand side is now negative 4. Let's make a bit of space and continue. Okay, so to get rid of a logarithm, as we saw in the previous example, we are going to have to raise both sides of the equation to the power of e. So left-hand side now becomes e to the power of negative 4x, and the right-hand side, when we've raised it to the power of e, the logarithm is now gone, so we have y plus 3 over 8. Okay, almost done now. We're just going to push the 8 across the other side, and now because e to the power of anything is always positive, and 8 is always positive, we don't really need these absolute values anymore because this is always going to be giving us a positive value. So we don't really need to consider them any further, and we can just kind of forget them. Okay, to finish it off, we're just going to minus the 3 across the right-hand side, and now we have y as our subject, and we've evaluated our solution to this differential equation as y equals 8 e to the minus 4x minus 3. Okay, brilliant. To finish off, one more example before we do an HSC question. Similar style again, we have a differential equation in terms of y. We have some initial conditions of when x is equal to 0, y is equal to pi on 4. If the last two examples have made some sense to you and you want to have a crack yourself, by all means, hit pause and try running through this one by yourself. But if that's not your style and you just want to watch and learn, well, hey, I can't stop you. Let's dive into it. Starting off with our first step, as always, from the last two, is to flip both sides to get our reciprocals. So we're going to be saying left-hand side is now dx on dy. Right-hand side is 1 over cos squared. Now, conveniently, 1 over cos squared can be written as sec squared because sec is the reciprocal of cos. So we have 1 dx on the left-hand side, multiplied the dy across the right, and now written the 1 over cos squared as sec squared. Now we're ready to do some integration, integrating both sides. The integral of 1 with respect to x is just x, and hopefully you are aware that tan differentiates to sec squared, which means that the integral of sec squared is going to give us tan. So we end up with x plus constant is equal to tan of y, and now we can just dive straight in and figure out what our constant is using the information in the question. The question says that when x is equal to 0, y gives us a value of pi on 4. So we're going to make x equal to 0 on the left, and we're going to put y equal to pi on 4 on the right hand side. This very quickly gets us the value of c because tan of 45 degrees is just 1, so we get c is equal to 1. Okay, we can put that back in over here, and then just for a bit of practice, we will make y the subject. We have tan y, but we want to get y. So in order to get rid of the tan, we're going to have to do inverse tan. So we get y is equal to inverse tan of x plus 1 as our solution to this differential equation. Okay, now we're up to the final one, which is a relatively easy band 3 question from the 2020 HSC for 2 marks. By all means, pause and have a crack if you want to have some fun. Otherwise, let's run through it together. Okay, starting off by, as always, because the right-hand side is in terms of y, and y is on the top of our fraction, we need to take the reciprocal of both sides. So dx on dy on the left-hand side. Right-hand side is now 1 over e to the 2y. We can now multiply our dy across, so we have it in the right spot for our integration. If we want to integrate 1 over e to the 2y, we can put it into index form by using a negative power. So we can write this as e to the power of minus 2y, just so it's ready to do some calculus as we prepare to integrate both sides. Okay, left-hand side is of course going to integrate to x, and we can put our constant there. On the right-hand side, if you want to integrate an exponential function, we need to keep this function the same and just remember to divide by the derivative of the power. Now the derivative of negative 2y is negative 2. So I'm keeping the e term the same, but I'm dividing it by minus 2. Okay, that's probably pretty close to an answer. We want to get x as a function of y, which means we want to make x the subject. So we're just going to put that constant across to the right-hand side. Again, moving that across, I don't need to make it negative because I don't really know what the value of c is. So c can be plus or minus on the right-hand side until we figure out what it is. So we can just put it anywhere. And then if we want to, we can rewrite this as 1 over e to the 2y, but either of these two forms for our answer is going to be getting us the marks. But there's my best version for the answer, -1 over 2e to the 2y plus c for the 2020 band 3 question. Okay, that about wraps it up for the intro video for differential equations. I'll be doing another one of these in a couple weeks and looking at some more difficult and more complex separable equations. So please stay tuned if you're wanting some more help with those. And yeah, hope to see you in future videos for the Extension 1 course, and plenty more revision coming up leading up to the HSC and maybe your trial exams. But thanks for joining me. Hope you got some value out of that, and I'll catch you in some future videos. Bye for now, not forever.